Hello and welcome. Today, we are rewriting the textbook on interstellar visitors. For years, the scientific community has operated under a specific set of assumptions regarding objects that enter our solar system from the vast emptiness between stars. We assumed they would be cold, inert, or at best, faintly active remnants of distant planetary formation. We assumed they would behave like the comets we know, dirty snowballs waking up as they approach the sun. But today, as we look at the latest telemetry coming from the Japan Aerospace Exploration Agency, or JAXA, we have to admit that the universe has thrown us a curveball. The object known as 3I Atlas, or C2025N1, has just done something that no interstellar object has ever done before. It has lit up the high-energy spectrum. We are talking about X-rays. This is a fundamental shift. Until December 10, 2025, 3I Atlas had been observed in every wavelength we typically use for cometary study. We had data in the ultraviolet, visible light, infrared, submillimeter, and radio wavelengths. We had a complete spectral picture that, while unusual, fit within the boundaries of known physics. But the detection of X-ray emissions changes the game entirely. This is not just a minor footnote in an astronomical journal. It is a signal that high-energy physics are at play in the immediate vicinity of an object that should be, by all accounts, a frozen rock. Before we dive into the specifics of this detection, if you want to stay ahead of these breaking developments in interstellar research and deep space astrophysics, make sure you are subscribed to the channel. We are tracking this story hour by hour, and you won't want to miss the analysis of the spectroscopic data coming in next week. Now, let's look closer at the data. The detection comes from the XRISM mission, the X-ray Imaging and Spectroscopy mission, led by JAXA in collaboration with NASA. Specifically, the data was captured by the Xtend soft X-ray imaging telescope. This instrument is a marvel of engineering, designed to capture the universe's most energetic events, from galaxy clusters to supernova remnants. It was never primarily intended to hunt for emissions from a single small comet drifting through our solar system. And yet, when the telescope was slewed toward the coordinates of 3I Atlas, the CCD imager, which covers a massive 38.5 arc-minute field of view, registered a distinct, undeniable signal. This contradicts what we previously thought about the energy budget of interstellar comets. Typically, comets are cool bodies. They reflect sunlight and emit thermal radiation in the infrared. When they get close to the sun, ices sublimate, releasing gas and dust. We see fluorescence in the visible spectrum, but X-rays? X-rays require high-energy interactions. They require temperatures in the millions of degrees or particle collisions of immense velocity. Finding X-rays coming from a comet is like finding a neon sign glowing in the middle of a dark, uninhabited desert. It implies an external power source or an interaction we hadn't fully accounted for. To be fair, X-ray emission from comets is not entirely unprecedented in the history of astronomy. We first saw it in 1996 with Comet Hyakutake. That discovery was a shock at the time, eventually explained by a process called charge exchange, where highly charged ions in the solar wind collide with neutral atoms in the comet's atmosphere, stealing electrons and emitting X-ray photons in the process. Since then, we've seen it in other solar system comets. But here is the crucial detail. 3I Atlas is not a solar system comet. It is an interstellar object. It formed around a different star in a different chemical environment, perhaps billions of years ago. We have never, in the history of observing interstellar objects, which, granted, is a short history starting with Oumuamua and Borisov, seen one generate an X-ray signature. The fact that 3I Atlas is doing so suggests that its coma, the cloud of gas surrounding the nucleus, is significantly denser or more complex than our initial models predicted. For the solar wind to interact with the coma vigorously enough to produce a detectable X-ray glow at this distance, there must be a substantial target for those solar wind ions to hit. The neutral gas density has to be high. This implies that the sublimation rate of 3I Atlas is far higher than what we would expect for a standard comet at its current heliocentric distance. It is pumping out gas at a prodigious rate. So, what does this actually mean? It means we are not looking at a simple rock. We are looking at an engine of sorts, a dynamic system that is interacting violently with the space environment of our solar system. The Xtend image reveals a projected region of emission about 3 million kilometers across. Think about that scale. The nucleus of the comet is likely only a few kilometers wide, yet it is influencing a volume of space 3 million kilometers in diameter, creating a structure of high-energy interaction that dwarfs the planets. The implications for the composition of the comet are profound. If the mechanism is indeed charge exchange, then the efficiency of this process depends heavily on the specific chemical makeup of the gas in the coma. Different gases have different cross-sections for interaction with solar wind ions. The intensity of the X-rays we are seeing might be telling us that 3I Atlas is dumping a specific type of gas, perhaps water vapor, perhaps carbon monoxide, or perhaps something more exotic, in vast quantities. We are waiting on the high-resolution spectroscopy from XRISM's other instrument, Resolve, to tell us exactly what those ions are. But the mere existence of the image from Xtend is a smoking gun. It tells us that the interaction between this interstellar visitor and our home star is far more energetic than we anticipated. It suggests that the shield of gas around the comet is thick and robust. This finding also forces us to re-evaluate the thermal history of the object. If it is outgassing this heavily, it must have retained a significant reservoir of volatiles despite its long journey through interstellar space. How did it hold on to these ices? Was it ejected from its home system recently, or has it been traveling for eons, protected by a crust that has only now cracked open? The X-ray data is the first tug on a thread that might unravel the entire history of this object. As we move forward in this analysis, we need to keep in mind that X-rays are a proxy for violence. They represent high-energy collisions. 3I Atlas is not quietly drifting through the night. It is crashing through the solar wind, creating a shock wave of energy that we can see from Earth orbit. It is a chaotic, active event, and as we will see in the next chapter, the shape of this X-ray emission is just as puzzling as its existence. It's not a uniform sphere. It has structure, it has direction, and that structure might hold the key to understanding the internal forces tearing this comet apart. We have established that the invisible spectrum has revealed a hidden layer of activity. But to understand the mechanics of that activity, we need to map the glow. We need to look at the geometry of the X-rays and see what they tell us about the magnetic environment and the flow of the solar wind around this intruder. That is where the story gets even more interesting and where the physics starts to challenge our standard models of cometary interaction. As we established in the previous chapter, the detection of X-rays from 3I Atlas has fundamentally altered our perception of this interstellar visitor. It is no longer just a passive traveler. It is an active participant in a high-energy collision with our solar system's environment. But simply knowing that X-rays are present is not enough. To truly understand what is happening, we have to look at the shape of the signal. We have to map the glow. The data from the Xtend instrument on JAXA's XRISM satellite provides us with a spatial map of this emission, and the geometry is revealing. The image spans a projected region about 3 million kilometers across. To put that in perspective, that is roughly 8 times the distance from the Earth to the Moon. This is a massive structure, but the emission is not evenly distributed across this 3 million kilometer canvas. The core of the X-ray glow, the region of highest intensity, extends roughly 400,000 kilometers from the comet's nucleus. Let's look closer at the data. The emission is offset. It is not a perfect sphere centered on the comet. Instead, it is crescent-shaped, bowing out toward the sun. This morphology is the classic signature of a bow shock. It confirms that the primary mechanism at play is indeed the interaction with the solar wind, the stream of charged particles flowing out from the sun at hundreds of kilometers per second. When this supersonic wind hits the obstacle created by the comet's coma, it slows down, compresses, and heats up. However, the scale of this interaction region is what is raising eyebrows. For a comet of this estimated size, the coma should not be dense enough to create such a distinct and extended X-ray bow shock at this specific heliocentric distance. The standoff distance, the point where the pressure of the solar wind balances the pressure of the expanding cometary gas, is much further out from the nucleus than standard models would predict for a typical comet. This contradicts what we previously thought about the density of the gas cloud surrounding 3I Atlas. For the bow shock to form 400,000 kilometers upstream, the comet must be pumping out gas at a rate that rivals the most active solar system comets we have ever observed, like Hale-Bopp. But 3I Atlas is a relatively small object. Where is all this gas coming from? The volume of the coma suggests an explosive release of volatiles, a continuous eruption that is inflating a massive bubble of gas around the nucleus. Here is the crucial detail. The X-ray spectrum obtained by the Resolve instrument, the spectrometer on board XRISM, shows distinct emission lines. These are the fingerprints of specific ions. We are seeing strong lines from highly ionized oxygen and carbon. These are solar wind ions that have captured electrons from the neutral gas in the comet's coma. The intensity of these lines tells us about the efficiency of the charge exchange process, and the efficiency is off the charts. So, what does this actually mean? It means the neutral column density, the thickness of the gas cloud, is incredibly high. It suggests that the gas is not just expanding freely into space. It might be confined or magnetically channeled in some way, or simply that the production rate is spiking violently. This brings us to a fascinating comparison. When Comet Hyakutake was observed in 1996, it also showed a crescent-shaped X-ray emission. But Hyakutake was a large, active comet passing very close to Earth. 3I Atlas is an interstellar object, likely smaller and further away. For it to mimic the X-ray signature of a giant like Hyakutake implies that 3I Atlas is punching above its weight class. It suggests that the surface composition of this object is incredibly volatile rich. It's not just a rock with some ice. It might be a chunk of almost pure frozen gas, sublimating furiously as it feels the heat of the sun. I want to pause here and ask you a question. If this object is releasing gas at such a phenomenal rate, do you think it can survive its passage through the solar system? Or are we watching it disintegrate in real time? Let me know your thoughts in the comments below. Is this a dying gasp or a standard feature of interstellar objects we just haven't seen before? Building on this idea of disintegration, the X-ray map shows something else, a slight asymmetry in the tail direction. The X-ray glow trails off behind the comet, as expected, but there are knots of brightness, localized hotspots within the tail. These could be interpreted as plasma clouds or detached structures. This happens when the solar wind magnetic field lines drape around the comet and then disconnect, carrying chunks of the ionized tail with them. These disconnection events are dramatic. They represent a stripping away of the comet's atmosphere. If 3I Atlas is experiencing frequent disconnection events, it is losing mass rapidly. The X-ray data is essentially showing us the erosion of the comet. We are watching the solar wind strip mine the atmosphere of an object from another star system. The rate of this erosion, combined with the massive production rate required to sustain the bow shock, paints a picture of an object under extreme stress. The Xtend data also reveals a temporal variability. Over the course of the observation window, the X-ray brightness fluctuated. This isn't just a steady glow, it's flickering. This flickering could be due to changes in the solar wind density, gusts in the solar wind, so to speak, or it could be due to changes in the comet's output. If the comet is rotating and active jets are turning on and off as they move into sunlight, we would see pulses in the gas density, which would translate to pulses in the X-ray brightness. The periodicity of these fluctuations is currently being analyzed, but preliminary numbers suggest a fast rotation. A fast-spinning, highly active object is a recipe for structural failure. The centrifugal forces, combined with the pressure of the escaping gas, could be pushing 3I Atlas to the breaking point. This connects to the visual observations we will discuss later. The X-ray map is not just a picture of the solar wind, it is a map of the comet's internal engine. The size of the halo tells us the power of the engine. The shape of the halo tells us about the aerodynamics of the interaction. And the flickering tells us about the stability of the nucleus. We are seeing a soft X-ray glow, which means the photons have relatively low energy compared to hard X-rays. This is consistent with the charge exchange mechanism, but there is a faint, harder component that some researchers are arguing about. If confirmed, a hard X-ray component would require an even more energetic process, perhaps involving magnetic reconnection events within the comet's tail, miniature solar flares happening in the wake of the comet. The mapping of this glow has given us the boundary conditions for the physics of 3I Atlas. We know the scale of the coma, huge. We know the interaction strength, intense. We know the composition involves significant amounts of carbon and oxygen targets. But this external view is only half the story. To understand why the coma is so dense and why the comet is reacting so violently, we have to look at what is coming out of the nucleus itself. We have to look at the chemistry, and that is where NASA's findings on nickel and gas jets come into play. The X-rays are the smoke. Now, we need to find the fire. Given what we now understand about the massive X-ray halo surrounding 3I Atlas, we are left with a burning question. What is fueling this engine? The X-ray data tells us there is a massive cloud of gas, but it doesn't tell us exactly what is driving that gas off the surface with such ferocity. For that, we turn to a different set of instruments and a new set of puzzles. This brings us to the chemical analysis, and specifically, the nickel mystery. NASA researchers, utilizing high-resolution spectroscopy from ground-based observatories and the James Webb Space Telescope, have reported unusual signatures in the comet's coma. The most striking of these is the presence of atomic nickel vapor. Now, finding metals in comets is not entirely new. We've seen iron and nickel vapors in solar system comets before, usually when they are very close to the Sun, where temperatures are high enough to vaporize metal. But 3I Atlas is not grazing the Sun. It is still at a distance where temperatures should be far too low to sublimate solid nickel. This contradicts what we previously thought about the thermal limits of cometary activity. Standard sublimation involves ices, water, carbon monoxide, carbon dioxide, turning into gas. These happen at low temperatures. Nickel requires temperatures over 1,000 degrees Kelvin to sublimate from a solid metal state. 3I Atlas is nowhere near hot enough for that. So, what does this actually mean? It means the nickel is not coming from the sublimation of solid metal chunks. It must be coming from the breakdown of a special kind of molecule, an organometallic complex, or a sulfide that contains nickel but is volatile at low temperatures. This suggests a chemistry that is radically different from the standard dirty snowball model of our solar system. It implies that the environment where 3I Atlas formed had a unique chemical inventory, perhaps rich in complex metal-bearing molecules that we rarely see in our own backyard. But the mystery deepens. The nickel signature is not uniform. It appears to be associated with specific, powerful gas jets. These are not the gentle, diffuse outgassing we see in some comets. These are collimated streams of material blasting out from the nucleus. The velocity of the gas in these jets is higher than expected, suggesting a propulsive mechanism that is more energetic than simple thermal sublimation. Let's look closer at the data regarding these jets. NASA reports indicate that the jets are intermittent but explosive. They turn on and off. This behavior points toward a cryovolcanic process. Imagine pockets of high-pressure gas, perhaps carbon monoxide or nitrogen, trapped deep beneath the surface of the comet. As the heat from the sun penetrates the crust, the pressure in these pockets rises until the crust fails. The gas explodes outward, carrying dust and these mysterious nickel-bearing molecules with it. This is not just melting ice. This is a geological eruption on a miniature scale. If 3I Atlas is riddled with these high-pressure pockets, it explains the massive coma density we saw in the X-ray data. The comet is essentially a pressure cooker that is blowing its lid repeatedly. Here is the crucial detail. The ratio of nickel to iron in these signatures is skewed compared to solar system values. In our solar system, iron is usually much more abundant than nickel. In the spectra of 3I Atlas, the nickel lines are surprisingly strong relative to iron. This abundance anomaly is a fingerprint of the star system where this object was born. It suggests a different nucleosynthetic history, a different mix of elements in the nebula that formed 3I Atlas. We are literally sampling the dust of a foreign star. The presence of these powerful jets also complicates the orbital dynamics. We know that outgassing acts like a rocket thruster, pushing the comet. This is called the non-gravitational acceleration. For most comets, this is a subtle effect, but with jets this powerful, the effect on 3I Atlas's trajectory could be significant. It makes predicting its exact path more difficult, and it adds a chaotic element to its motion. Some researchers are proposing that the nickel might be released through a process called photodissociation of short-lived molecules. But the speed at which the nickel appears in the coma suggests the parent molecules are breaking down very quickly after leaving the nucleus. This points to a very fragile, unstable surface composition. The combination of the X-ray halo and the nickel jets paints a picture of an object that is chemically exotic and physically volatile. It is not a solid, monolithic rock. It is likely a porous aggregate, a fragile lattice of ices and strange chemical compounds that is crumbling under the thermal stress of our Sun. This connects to the structural integrity of the object. If you have powerful jets blasting out from the interior, you are excavating the comet from the inside out. You are creating voids. Eventually, the structural integrity will fail. We might be witnessing the prelude to a fragmentation event. The nickel mystery might be the evidence of the comet's internal support structure dissolving. Furthermore, the detection of these metals at such large heliocentric distances challenges our understanding of how heavy elements are distributed in planetary systems. If metal-bearing molecules can be locked into ices and transported across interstellar space, it suggests a mechanism for seeding heavy elements into forming planetary systems that we hadn't fully appreciated. 3I Atlas is a carrier of complex chemistry. As we analyze the spectral lines of the nickel, we are also looking for other metals. Is there platinum? Is there gold? While unlikely to be found in veins like on Earth, the atomic signatures of these heavy elements would tell us about the supernova environment that enriched the birth cloud of this comet. The internal factory of 3I Atlas is churning out materials that are baffling our best chemists. But while the chemistry is strange, the physical structure that these jets are creating is even stranger. The jets are not just spraying gas randomly. They seem to be creating a specific shape, a morphology that has caught the eye of high-resolution imagers. And one feature in particular has sparked a debate that goes beyond standard cometary physics. It involves a structure that looks less like a tail and more like a shield. This leads us directly into the controversial and fascinating observations from the HiRISE camera. Building on the discovery of the powerful nickel-rich jets erupting from 3I Atlas, we must now turn our attention to the large-scale structure these jets are creating. We have looked at the invisible X-rays and the chemical fingerprints. Now, we look at the physical shape of the object as seen by our sharpest eyes in the sky. And this is where the story takes a turn into the truly unconventional. High-resolution imagery, including data processed from NASA's HiRISE instrument, usually pointed at Mars but repurposed for this deep space observation, has revealed a peculiar morphology. Most comets have a tail that points away from the Sun, driven by the solar wind and radiation pressure. 3I Atlas has that, but it also has something else, a forward-facing expansion. Let's look closer at the data. The images show a diffuse cone-like structure extending ahead of the nucleus, aligned with the comet's direction of motion. This is highly unusual. In standard fluid dynamics, moving through the interplanetary medium should sweep material back. To have material extending forward against the flow requires a significant ejection velocity. It implies that the most powerful jets we discussed in the previous chapter are not just random, they are clustered on the leading face of the comet. This contradicts what we previously thought about the random distribution of active regions on tumbling cometary nuclei. While sunward fans are known, this structure appears stable and highly collimated. It looks less like a spray and more like a coherent feature. Here is the crucial detail. The alignment of this forward structure is precise. It is not just roughly sunward. It is aligned with the velocity vector of the object. This coincidence has triggered a wave of interpretation, ranging from the conservative to the highly speculative. The mainstream scientific explanation is that we are seeing a dust shell phenomenon. If the comet is rotating in a specific way, and a particularly active vent is located near the pole that faces the direction of motion, it could continuously pump material forward. This material eventually curves back due to solar radiation pressure, creating a parabolic hood or shell around the nucleus. We have seen similar structures in comets, like Hale-Bopp. The forward-facing nature is an optical illusion of projection and the dynamics of the dust grains. However, some interpretations go further. This is where the conversation shifts to the ideas proposed by astrophysicist Avi Loeb and his colleagues. After analyzing the high-contrast imagery and the stability of this forward structure, Loeb noted a resemblance to a magnetic shield or a particle beam configuration. The speculative idea here is fascinating. Loeb suggested that, in principle, if an artificial object were traveling through interstellar space, it might employ a forward-facing emitter, a beam of particles or light, to clear micrometeoroids and dust from its path. At relativistic or high velocities, interstellar dust hits like bullets. A shield is necessary. The structure we are seeing on 3I Atlas, with its forward expansion, mimics the geometry of such a clearing mechanism. So, what does this actually mean? To be clear, this is not the mainstream view. The scientific consensus remains firmly on the side of natural cryovolcanism. But the fact that the data allows for such a calculation to even be made illustrates the degree of strangeness we are dealing with. The shield hypothesis is a mathematical fit for the morphology, even if the physical requirements, an artificial power source, are absent from our detection. This speculative angle highlights the unconventional behavior of the object. Even if we dismiss the artificial hypothesis, the natural explanation requires a set of conditions, spin axis, vent location, jet velocity, that is statistically rare. It means 3I Atlas is a perfect storm of cometary physics. The forward structure also has implications for the X-ray bow shock we discussed in Chapter 2. If the comet is injecting high-velocity gas directly into the oncoming solar wind, this would enhance the bow-shock interaction. It explains why the X-ray halo is so extended and intense. The comet is not just passively hitting the solar wind, it is actively firing into it. This head-on collision between the cometary jets and the solar wind creates a region of extreme turbulence and heating, maximizing the X-ray production. We also have to consider the drag effects. A forward-facing jet acts as a brake. It exerts a thrust force opposite to the motion. If this structure is persistent, 3I Atlas should be slowing down more than gravity alone would dictate. We are currently analyzing the astrometric data to see if this deceleration is detectable. If it is, it would confirm the rocket nature of this forward plume. The existence of this structure forces us to ask, is this a temporary feature, or has 3I Atlas maintained this orientation for a long time? If it is stable, it implies a very specific internal mass distribution that keeps the rotation axis fixed. It suggests the object is not tumbling chaotically, but spinning like a gyroscope. This connects to the panspermia engine concept. If comets like this can shield their interiors with massive outgassing and bow shocks, could they protect biological materials deep inside from cosmic radiation? The forward shield, whether natural or otherwise, acts as a buffer. It creates a protected wake behind it. As we stare at these high-rise images, we are seeing the silhouette of a traveler that refuses to fit into our standard boxes. It has the X-ray signature of a giant, the chemistry of a stranger, and the shape of a dart. The forward shield is the visual manifestation of its dynamic resistance to the solar system environment. We have covered the spectrum, the map, the chemistry, and the shape. Now we must pull all these threads together. What is 3I Atlas? Is it a freak of nature, a rare roll of the cosmic dice? Or does it represent a new class of object entirely, a type of interstellar visitor that we are only just beginning to perceive? In the final chapter, we will synthesize these findings and look at the new physics that 3I Atlas is forcing us to consider. We have journeyed through the invisible spectrum of X-rays, mapped the colossal glow of the bow shock, dissected the impossible nickel chemistry, and analyzed the peculiar forward-facing shield. Now we arrive at the synthesis. We must ask the ultimate question: what is 3I Atlas? The data we have gathered since December 10, 2025 suggests that 3I Atlas is not merely an anomaly. It is a prototype for a new class of interstellar object. It challenges the binary categorization of comet versus asteroid that we have relied on for decades. It is something more dynamic, more complex, and physically more extreme than anything we have encountered before. Let's look closer at the data one last time. We have an object that generates X-rays through intense solar-wind interaction, Chapter 1 and 2. We have an object that releases nickel and other metals via low-temperature cryovolcanism, Chapter 3. We have an object that maintains a stable, forward-facing jet structure that mimics a shield, Chapter 4. This contradicts what we previously thought about the passive nature of interstellar debris. We assumed these objects were dead remnants. 3I Atlas behaves like an active machine, a natural machine, fueled by the heat of stars, but a machine nonetheless. It processes its environment. It reacts. It fights back against the solar wind. Here is the crucial detail. The combination of these traits suggests that interstellar comets are fundamentally different from solar system comets. They are not just Oort cloud objects that got lost. They are formed in environments with different chemical abundances, different radiation histories, and different structural properties. 3I Atlas might be a shard of a super-Earth or a mini-Neptune that was shredded by tidal forces, retaining a core of volatile, rich, metal-infused exotic ices. So, what does this actually mean for the future of astrophysics? It means we need new physics to describe the sublimation of these exotic materials. We need new models for the magnetospheres of small bodies. We need to rewrite the book on how solar wind interacts with non-standard atmospheres. The new physics of 3I Atlas is a physics of extremes. It is the physics of hyper-volatile ices that explode rather than melt. It is the physics of dusty plasmas creating X-ray auroras around a rock. It is the physics of interstellar transport. Some researchers are now proposing that objects like 3I Atlas are the primary vectors for panspermia, the spreading of chemical precursors to life across the galaxy. The protective shield we observed, the rich chemical inventory, the violent outgassing, these are all mechanisms that could, in theory, transport complex organic molecules safely between stars. 3I Atlas is not just a visitor, it might be a seed. The speculative ideas we touched on, the artificial alignment, the particle beam analogy, while not proven, serve a vital scientific purpose. They force us to look for the boundaries of the natural. By proving that 3I Atlas is natural, we learn exactly what nature is capable of. We learn that nature can build structures that look artificial. We learn that nature can create engines. As 3I Atlas speeds away from us, heading back into the dark, it leaves us with a transformed understanding of our universe. We now know that the space between the stars is not empty. It is filled with these active, glowing, hissing travelers. We know that if we look with the right eyes, with X-ray telescopes and high-resolution spectrometers, we will find them. This discovery is just the beginning. The Vera Rubin Observatory is coming online. The Comet Interceptor mission is waiting in the wings. We are entering the golden age of interstellar object research. 3I Atlas was the wake-up call. If you found this deep dive fascinating, if you want to support science communication that doesn't shy away from the complexity, please hit that like button. It helps the algorithm find other curious minds like yours. And tell me in the comments, do you think 3I Atlas is a rare oddity? Or is the galaxy teeming with these X-ray emitting travelers? Thank you for watching. Keep looking up.